So if we look at the work done on a rotating object, we can do that similarly to what we did before. We can look at, let's say we're pushing this object. We have a certain amount of force, over a displacement. We can find work. So force times displacement. We have a certain axis of rotation here, and so we've got that there. Distance, remember, is r omega. So like we looked at before here, let's say we have 2 radians, right? 2 radians, which would mean 2, and let's say this is 1 meter long, right? So this would be a meter, this would be a meter. So 1 meter times 2 radians is 2 meters of the distance, right? Okay, so work is force over whatever this radius is times theta, right? So force over a radius is torque, and so therefore we can find out how much work is done based on multiplying the torque times the rotation amount there. And then power, we can find power just taking the work done over time. And we know that omega is how much, angular displacement in time. So power is torque times omega. So with these equivalents, we can do similarly to what we did with the kinematic equations. We know linear motion here. We have force equals ma. We have torque is equal to I alpha, right? So we've already done that. And then work equals force times displacement. And then now work, we can look at work as torque times the times theta. And then the last one is force times the speed, which we can get torque times omega as well. So now we have a wheel that we're going to look at. Let's say we have a force of 26 newtons that we apply to this wheel, and it begins to roll, and it goes forward. The radius is 0.41 meters. And let's say that we push for 29 radians. How much work do we do? So yeah, go ahead and pause the clip and calculate the work that we do. And when you're ready to check, you can hit play to continue. All right, so the equals our theta. We have our work. The radius is 0.41 meters. The radians is 29. So 11.89 meters. And we have the force. So we get the amount of work, 309 Newton meters of work. So if it took 15 seconds, what's the power output here? And so we can look at that. So go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so we should get 20.6 watts of power. It took 15 seconds for this to go across. Now, let's say that this is a ring shape and we have a mass of 7 kilograms. How fast is it moving after we push it with 26 newtons? And so we've got our moment of inertia. We have our ring, which is mr squared. And so yeah, we can figure out, using the work equals the change in kinetic energy, we can figure out the final speed. How fast is it moving angularly after this push? So go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so we should get 22.9 radians per second is the angular speed, and as it goes, and how fast linearly is that? So go ahead and pause the clip and do that. When you're ready to check, you can play to continue. All right, so should get 9.398 meters per second linearly. That's how fast it's going. Now that we have our wheel that's spinning at 22.92, let's say that we're coasting to a stop, and let's say the resistive force is 6 newtons. How far is it going to go in radians until it comes to a stop? And so
This one's a bit of a review because you're going to have to go back to looking at how torque affects acceleration. So yeah, go ahead and pause the clip and give that a try. When you're ready to check, you can hit play to continue. All right, so torque equals I alpha, and we have our force, which is 6 newtons. Our radius is 0.41 meters, and the moment of inertia is 1.1767. The acceleration is negative 2.09 radians per second squared. Now that we know that, we know the angular acceleration, we know the initial angular speed, we know the final angular speed, and we can calculate how far it goes, and it should go 125.67 radians. All right, so how much work is that? So go ahead and pause the clip and do that and calculate the work, and when you're ready to check, you can hit play to continue. All right, so D equals R theta, and so it's going to go 51.5 meters as it travels, and 6 newtons, so 390 newton meters is the work that is done, which should make sense because that's how much work it took to get it up to that speed. That's how much work it's going to take to slow it down to a stop. So how much power is that? Go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so we have to find the time, and the time is 10.97 seconds, and therefore the power output is 28.18 watts.
All right, so let's say we have this disc that has a moment of inertia of 25 kilogram meters squared, and the radius is 0.8 meters. And let's say it's rotating at 320 revolutions per minute, and it must be stopped in 12 seconds. So we need to figure out the work needed to stop it, and then we can find the power developed in stopping it as well. And then we can determine the torque that stopped the disc. So we'll go ahead and draw it out. We know that work done is equal to the change in kinetic energy, so that can be helpful. The initial kinetic energy, we have a certain amount. The final kinetic energy is 0. So the initial kinetic energy is 1/2 I omega squared. So the moment of inertia, we're looking for a disk. And omega is in radians per second. So 320 revolutions per minute, we need to get that into radians per second. We know one full revolution is 2 pi radians, so 2 pi radians, 6.28 radians about. So, 1 radian, 2 radians, 3, 4, 5, 6 and a little bit more. And we end up getting 33.5 radians per second. That's the initial angular speed. And so we've got that in there, and we know that the moment of inertia for this disk, and so therefore we can get how many joules it's going to take to slow this down. And that's the work needed to stop it. And so therefore, over 12 seconds, we can get the power needed to stop it, so 1,169 watts. And so this is average power because it's starting with a maximum, right, as we start to stop this, but then at the end the force is 0, the kinetic energy is 0, so it's no power at the end. So again, this would just be average power. So average power is equal to torque times the average angular speed, and so the average would be right in between 33.5 and 0, so 16.75 radians per second. So therefore the average amount of torque would be 70 newton meters. Now another way to look at this with the using kinematics, we're dealing with the angular speed of 33.5 radians per second. We can look at alpha, which is the change in angular speed over time, and we find that it's negative 2.8 radians per second squared is the average angular acceleration, or is just the angular acceleration over that time. And so therefore We know that the force times the radius, which is torque, equals the moment of inertia times alpha. And we end up getting 87.5 newtons for the force. And yeah, we have a torque of 70 Newton meters. And so we can look at it that way as well. All right, so when we talk about angular momentum, this is another parallel that we're dealing with here, where we have an object that's rotating about a fixed axis, and we can evaluate it based on similar to what we did with momentum, but now the momentum of an object that's actually rotating. So the way we calculate angular momentum is we take the moment of inertia and we multiply it by the angular speed, and then we end up getting the angular momentum of kilogram meters per second squared. So if we consider a point mass at a certain radius, we know the linear speed is r omega, so the radius times the angular speed, and we know that the angular momentum is I omega. And so for a point mass, it's mr squared. And if we solve for, omega, we have the linear speed over r. And so therefore, if we're looking at the angular momentum, it's mr squared v over r. The two r's will cancel out there. So mvr will be the angular momentum. And this can be helpful because, this is in terms of linear, what's the linear motion, the tangential velocity here, right? Whatever it is, and that will give us, an angular momentum.
So let's apply this to a ball that's being swung in a circle, a singular point mass that's swinging in a circle. The mass is 0.12 kilograms and the radius is 0.43. Let's say it's going 32 radians in 1.7 seconds. We want to find the angular momentum. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we know the angular momentum equals I omega. We have our point mass, which is mr squared, and we cover 32 radians in 1.7 seconds, so 18.82 radians per second. And therefore, we get an angular momentum of 0.418 kilogram meters squared per second. Let's go ahead and try this with a ring that's spinning. And the ring has a radius of 3 meters. The mass is 16 kilograms, and the linear speed is 2.5 meters per second. We want to find out the angular momentum of the ring. So yeah, go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. All right, so we know V equals r omega, and we can find the angular speed, 0.833. And we can find the angular momentum, which is mr squared for a ring times the angular speed, and we should get 119.952 or 200 or 120 to be exact, kilogram meters squared per second.
So now if we consider a disk, we know that a force will cause the rotation here at the outer extent there. Over a period of time, we have the radius there, and so the force times the radius will give us a certain amount of torque. And then with the change in angular momentum, we know that it's going to take a certain amount of torque over a period of time. And so this is similar to where we looked at before with a change in angular momentum, and we can determine what's going on with that in a dynamic situation. All right, so let's say we have a disk that's starting from rest, and so omega initial is 0. And let's say we apply force in this disk, and let's say the force is 15 newtons, and let's say that the radius here from here to here is 0.5 meters. And let's say we apply this force for a period of 20 seconds. And we want to find out, what's the the final angular speed, right? And so we know that the change in L is equal to torque times how much time we apply, T. So we know torque is 15. Well, it's force times the radius, right? So 15 newtons times 0.5 meters. And then over a period of time, 20 seconds. So the change in angular momentum, so 15 times 0.5 times 20 is 150. And kilograms meters per second squared. Okay, so the so with that we can figure out what's the final angular change as well. And so we have I omega final minus I omega initial equals 150 kilograms per second squared. So let's say for this disk that this disk had a moment of inertia of 20, we'll say. We could, and we know the initial angular speed was 0, and so we have 20 times omega final, which we're looking for, and equals 150. So the final angular speed in this case would be, let's see, 7.5 radians per second.
So let's look at this example where we had the ring again, and let's say that we have a resistive force of 6 newtons, and we want to find out how much time it's going to take to stop. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so the change in momentum equals torque times the time, and we know it's L final minus L initial, angular momentum final minus angular momentum initial. The final is 0, it's going to come to a stop. The initial is 119.952. We have our force and we have our radius, and the time that it's going to take is 6.664 seconds. Let's try this one. Let's say that this ball is swinging around. Let's say it takes 20 seconds to stop. What is the resistive force causing this to stop as it slows down? So yeah, go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. All right, so yeah, we've got our change in momentum equals torque times time. The final is 0, the initial is 0.418. And we're looking for the force, and so the force will be negative 0.0486 newtons. So one of the things that we consider as we consider about angular momentum is its conservation. If we have a jumper who's in the air and her arms are extended, and then she's in the air and she brings her arms in, we've all seen that where they start to rotate quite rapidly. And so why is that? Well, let's say the initial angular speed of this person is 7.5 radians per second, and their moment of inertia is 480. What goes into moment of inertia? Well, it's both how much mass you have, right? And then also what's your radius? And so if she brings her arms in, the moment of inertia drops. Now L equals I omega, where this is momentum, angular momentum. So if I drops, then angular speed, so I drops, angular speed must increase to compensate. And that's exactly what we see. And so, in the air, the person can bring their arms in. They're, in this case here, we're going to use this example where they're bringing their arms in and their moment of inertia drops to 365 from 480. And with that, she's going to speed up faster. And so what we do is we look at the L initial, and that should equal L final. As long as there's no outside forces, as long as there's no torque changing, or as long as there's no angular, any torque that's affecting the system. So she's in the air, she's spinning, there's no outside torque except for air resistance, which is going to be a little bit, but not a whole lot. And so, yeah, go ahead and pause the clip and calculate what her new angular speed must be if her angular momentum drops. All right, so we should get then the new angular speed should be 9.86 radians per second. And it's got to go up because her moment of inertia is decreased, and we've got that there. All right, let's go ahead and do this as well. If she takes 6 seconds to stop once she lands, how much torque is that that brings her to a stop? So go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. All right, so we've got the change in momentum equals torque times how much time it takes, and the amount of torque that would take would be 600 Newton meters would be how much it would take to slow her down to a stop.